Hello, students. We have learned titrations of weak acid with strong base and titration of weak base with strong acid. Okay, and now I summarized, the general case of titration of the polyprotic acid with a strong base. Okay, this is a general curve, and it says virtually everything. Okay, so if we understand this curve, okay, and then you will find it is very easy to solve any problems. Okay, based on this figure. All right. Okay, let's look at this figure in detail. And this x-axis is the added volume of strong acid, and y-axis is pH. Okay, as you see, since this is triprotic acid, theoretically it undergoes three um, titration regions. Was the first one. This is purple region 1, and this one, this fully protonated form of weak acid now reacts with strong base. Okay, and this is this region first, this region, the first equivalence point. Okay, here as you add a strong base, and then this form reacts first, and in this region you consume this one fully protonated form, and then you produce this one H2A minus, this anion. All right. um, and then you reach this first equivalence point. At this point, pH changes abruptly. Okay, and then you enter this second region, second buffer region. In this, I'm sorry, this is not purple 1, this is purple 2, I'm sorry. And in this region, since you already converted all H3A form to H2A minus form, and now this H2A minus anion reacts with hydroxide ion. Okay, and as you add hydroxide ion, and then you produce Ha2 minus ion. Okay, this is the the region 2, purple, second purple region. All right, and then you approach this second equivalence point. Okay, at this point you have only this form. Okay, Ha2 minus ion. Okay, now you enter the third region. Okay, that's the purple 3. I'm sorry, this is now 1, 3, and this one, this anion reacts with hydroxide ion, and then you produce A3 minus ion. Okay, yeah, and you pass this third equivalence point, and then after that, yeah, you have what, A3 minus and hydroxide ion. Okay, and from this figure, you will see the second equivalence point is just 2 times first equivalence point. Yeah? So you have to add exactly 2 times volume for the first equivalence point to reach the second equivalence point. And for the third equivalence point here, yeah, of course, you have to add 3 times the volume of the first equivalence point. All right. Yeah, this is very easy. And then now let's identify the principal species. Let's in first in the region, which is the the, principal species, and now let's see. Uh, Consider the halfway of first equivalence point here, right? And up to this point, the principal species is H3A. Okay, why? Although you produce this anion, but at the exactly the halfway of the first equivalence point, this one H3A form, the concentration of this species is greater than this one. Okay, yeah, and then passing through this halfway, and then this one is the most abundant species. Okay, and since these two species are present in the same solution, right? And this is what? This is a buffer. Okay, so buffer 1 now the equation is written this one as this one. pH equals pK1, okay, plus log and ratio of this anion and this fully protonated form. Okay, so uh, in order to obtain the K1 value, equilibrium post equilibrium constant of this triprotic acid, you simply find first the post equivalence point, and then here the you what point this one, the half of this post equivalence point, and then you read simply from this titration curve this pH. Okay, at this pH is exactly the same as pK1. Okay, because at this point the concentrations of the H2A minus and H3A are the same, so log 1 is 0. Okay, yeah, very easy. All right, so from here we know very important thing. How do we someone asked how we obtain equilibrium constant of weak acid or base. Okay, uh, yeah, we have many different ways. We You may apply some spectroscoping method, or you individually measure, for example here, this form and this form. Okay, by any means, but that requires a lot of efforts, and result is not so accurate. Okay, but if you understand this titration curve, it is very easy. Okay, why? Because you simply obtain this titration curve, and from this curve you simply read. Okay, you find out first the half of the first equivalence point, and then you read the pH value. That is pK1. Okay, very simple. Don't you think so? Yeah, right. Okay. All right. So we have first buffer in this region, and this is half of the first equivalence point, and the buffer capacity is maximum. Okay, because these concentrations are the same. All right. So it tells many things. Okay? And pH can be calculated, yeah, up by this equation up to this point. And what's the pH at this first equivalence point? At this point, we have only this anion. Okay, this anion is what? Hmm? This anion is can be acid or can be a base, because it can accept the hydroxide ion, or it can produce the proton. So this is the amphiprotic species. Okay, so uh, pH calculation now you already learned. Okay, so at first equivalence point here, proton concentration is given by this equation. Okay, so we can now calculate pH here, and then now if you keep adding the strong base, now we're entering the second region, yeah, second buffer region, up to this second equivalence point. Yeah. In this region, we have this anion, and then this one, Ha2 minus this anion. These two anions are present. Okay, so that is a buffer. So buffer equation is this one: pH equals pK2 plus log of the ratio of these two species. All right, very easy. Okay? So you don't have to do very complicated, the calculations. Okay, you simply use this one. Okay, and then you find out the added volume where here. Okay, and then this the ratio depends on how you where you are. Okay, and the halfway between the first and second equivalence points, at this point these two concentrations is the same. So at this point the pH is exactly pK2. Again, you see, to calculate the second equivalence point, you don't need to do anything. Simply you get this very precise titration curve and find out, this one, this point, and then you read from this curve the pH. Yeah? That pH equals pK2. All right. What is the principal species in this region? Okay, up to this halfway of the second equivalence point, still this H2A minus is the most abundant species, and then Ha2 minus form here. Okay, you understand? And what's the pH at this second equivalence point here? Yeah? pH is calculated by this equation. Since in this case, pK K2, okay, and K3 are both involved, okay, here. So pH calculation here, you have to use K2 and K3, okay, instead of K1 and K2, all right. So you use this equation to calculate pH here, all right. Now you enter the third region here, okay, passing the second equivalence point up to the third equivalence point, all right. The reaction is given here. Ha2 minus plus hydroxide ion produces A3 minus and water. Okay, here. Since these two species are both present in this region, that is also a buffer. Okay, that's the buffer 3, and pH is calculated by this equation. pH equals pK3 plus log and the ratio of these two species. All right, and also the exact the halfway between second and third equivalence point here, yeah, since the concentrations of these two species are the same, and then the pH here is exactly same as pK3. Okay, again, yeah, calculate obtaining the K3 is very difficult by other means, but you know when you the the obtain this titration curve, and then you simply read from this curve. Okay, yeah. So now you understand how this method is so powerful, yeah, to get not only what calculate pH, but also obtaining in K1, K2, and K3. All right, here. So this is exactly halfway. The purple capacity becomes maximum. All right, and at the third equivalence point, that's the point you have only A3 minus. Okay, this form. And then how to calculate pH? You simply take this one, this anion, as a monoprotic base, okay, weak base. I think you already know how to calculate pH at this point, okay. And then beyond this third equivalence point, and then the principal species are A3 minus and hydroxide ion, okay. Since the hydroxide ion is a much stronger base than A3 minus, also beyond this third equivalence point, the pH calculation only depends on the produced hydroxide ion, okay. Yeah, taking this ion as a strong base, okay. So basically, this is it. Okay? And I strongly recommend you to memorize, okay, this figure into your brain, okay, and then you will get much benefit. All right.